Welcome. In this video we're going to discuss a couple examples with triple integrals and triple integrals over tetrahedrons. There's two examples from the OpenStax book that I want to explain. The first one is example 5.38, and there's examples like this showing up in our homework. So they have the solution to both of these in there, and I'm just going to discuss the solution they gave to 5.38, and then afterwards I'm going to give an alternate solution to 5.39. Alright, so the problem here is evaluate the triple integral of the function 5x minus 3y over the solid tetrahedron bounded by the planes x equals 0, y equals 0, and z equals 0. That's just the coordinate axes. Okay, so, alright, and it's also bounded by the plane x plus y plus z equals 1. All right, and they've got the picture for that. All right, and so the region we're seeing here is in the first octant, and the way we set up a lot of these triple integrals is try to project that onto the y plane, and then that will lead to an iterated triple integral where our inside integral will be with respect to z. You don't have to do it that way, but that is kind of a convenient way for us to think because we're used to graphing z in terms of x and y. Now it's pretty clear in the figure that if we look at the projection onto the xy plane with the solid, well, it's going to be this triangle here. Let me just outline that in a different color. It's going to be a triangle in the xy plane, and one thing I just want to point out to you here is that this side here that I'm coloring in red is corresponding to this side over here, all right, which is along the x-axis, and this side here, let's do that in a different color, that I'm doing in green, that's along the y-axis. That kind of gets rotated, and this figure is vertical, shown over to the side. So the picture on the left, on the right side, is the XY trace, or the projection onto the XY plane. All right, and I'm just going to erase that now and discuss how we're going to think about parameterizing it. And the way I would do this would be to fix some generic x value between 0 and 1 in this case, and then we're going to let y vary as we're seeing in the picture from the bottom, which is y equals 0, up to the top. Alright, by doing that, letting x vary from 0 to 1 and y vary from 0 to 1 minus x, we can then let z vary from the bottom of the three-dimensional region, which I'll put now in red here, and then it'll vary, each point down here in the projection will vary z going from the bottom, which is z equals 0, up to the top, which is given by the plane z equals 1 minus x minus y. Alright, so that's why when you look at the solution for this problem, that's what you're seeing as a setup for the triple integral. I'm just going to write that down, and then we'll get to the next example. So for this problem, we would have the triple integral, and we were going to let x vary from 0 to 1. For each of those x's, we're going to let y vary from 0 up to the top, which was 1 minus x. That will cover every point in the projection region up here. For each xy point, then, we're going to let z vary from the bottom of the region, which is 0, up to the top, which is z equals 1 minus x minus y. And we obtain that by solving the equation x plus y plus z equals 1 for z. Alright, and the function we had was 5x minus 3y. So then we would have integrating 5x minus 3y, and this problem is a dz dy dx integral. And then you can look at the rest of the solution as far as how to work that out. The next problem I want to look at is the next example in the textbook, and it's also a tetrahedron, but it's a little bit different one than that one. It's saying to find the volume using a triple integral of this right pyramid. Alright, so this is like a tetrahedron, it's related to it, that has the square base in the xy plane given by the box negative 1 to 1, negative 1 to 1, and a vertex at 0, 0, 1 on the z-axis. The figure is shown down below here. Alright, now I'm going to give an alternate solution, and you can compare it to what you see in the OpenStax textbook. But what I'd like to do here is I would like to set this up as a dz as the inner integral. Alright, so we can project something onto the xy plane and then let z vary from the bottom, which is 0 in this case, to the top. Now we got to be a little careful to do this. We're going to have to use the symmetry involved here, and I'll just draw some of that on the figure. Underneath, I'm going to focus on this face right here. All right, underneath that face, what are we seeing? Well, underneath that face, I'm going to draw this down on the XY plane. We've got this triangular shaped, three-dimensional triangular shaped region. And what I want to do is I want to focus on finding that volume, all right, of that fourth of it, and then we'll just multiply that by 4 because the other sides are the same, or the other 4 pieces like that are exactly the same size. All right, so that's going to be our goal. And then we're going to accomplish that by finding a formula for this plane, which is representing that face, and that's what we need to write down. All right, and we're going to do that by using some techniques that we've learned earlier in the semester for how to find the equation of a plane via the cross product. Okay, so for us to do that, what we need to do is find two vectors in this plane so that we can use the cross product to find a normal vector. So I'm going to draw 3 points on here. One of them is what's already given, 0, 0, 1, and then these other 2 corners down below here. Let's write the coordinates of those down. All right, so we're assuming that this is x equals positive 1, this is y equals positive 1. All right, so therefore the coordinates of this point are 1, 1, 0, because we're in the xy plane. Here this is x equals negative 1, and the back is y equals negative 1. So this is going to be x equals negative 1, y equals positive 1, positive 1, and then z is equal 0. All right, so we know how to find, if we consider this, for instance, point A, and this point B, and this point C, we know how to write down the vector that connects the points A to B. It's going to be given by vector subtraction. So we want to write this vector down, and then likewise, we're going to write this vector down, which connects A to C. Okay, so let's write those out, and then we will take the cross product to find a normal vector to that face, which is going to, in that graph, is a plane, and therefore we're going to try to write the equation of that plane down. All right, again, that's our goal. Write down z equals what for this plane, which is representing the face, which is 1/4 of this pyramid. Okay, so let's write down those vectors. All right, so the vector that connects the points A to B, we've seen before, is given by vector subtraction. If we consider those points as vectors, what we're going to do is the vector 1, 1, 0 minus the vector 0, 0, 1, and that's going to give us the vector 1, 1, negative 1. And likewise, to connect A and C, we're going to do the vector subtraction with C minus A. All right, in that case, that's going to give us negative 1, 1, 0 minus 0, 0, 1. And that component-wise subtraction is going to give us negative 1, 1, negative 1. All right, now we need to do the cross product of those two vectors that we just found there. All right, so let's write those down. All right, and that's what we're going to define our normal vector to be. It's going to be the vector connecting A to B crossed with the vector connecting A to C. All right, and recall how to compute those cross products. A good way to remember to do that is with the 3x3 determinant, where we put ijk across the top row, 1, 1, negative 1, the components of the first vector we're taking the cross product in the second row, negative 1, 1, negative 1 as the components across the third row. Now we can do our cross product as we've done before. Remember, for the first one, for the first component, we cross off the first column and the first row, and then compute that resulting 2x2 determinant. All right, I'm just going to get rid of that highlighting there. And what is that going to give us? So what are we going to be doing? We're going to be doing negative 1 minus negative 1, which in that case is actually 0. All right, so we're going to get 0 here. All right, and then we got to take the opposite of what we get by deleting or covering up the middle column, first row. That's going to give us negative 1 minus 1, so that's negative 2. All right, so we're going to have minus negative 2. Remember, we have to negate that result. And then we're going to get, use my mouse here, 1 crossing off the first row, last column, 1 minus negative 1, which is positive 2. All right, so our normal vector is, or a normal vector to this plane is 0, 2, 2. Okay, now we know how to write the equation of a plane out. The equation of a plane is given by the formula ax plus by plus cz is equal to d, and we know that the normal vector's components are of a normal vector are the coefficients of a, b, of x, y, and z, which are a, b, and c. So we're going to have 0x plus 2y plus 2z is equal d, and we have to find that point out. So our equation becomes 2y plus 2z equals d. All right, now what we need to do is just plug any point we know is on the plane. I'm going to pick the point which was at the top of the pyramid, 0, 0, 1, and we'll plug that in for x, y, and z. So it'll be 2 times y plus 2 times z will equal d. We're plugging in 0 for y, 1 for d. That's going to give us that d is equal to. Alright, so therefore our equation becomes 2y plus 2z equals 2. We can divide both sides by 2, and that will simplify to y plus z is equal to. Alright, now that's going to give us the top of that face that we were looking at before. So we're going to have z is going to equal 2 minus y. Okay, I realize I just had a quick error there. When I divided both sides by 2, this should not have been a 2 on the right side. It should have been a 1. So this should be 1. Alright, so our equation is really z equals 1 minus y. Alright then, so we're still working on setting up the triple integral that's going to help us find this volume. Alright, I'm just going to look at the picture that we had here. So now we found the equation of this face here. The equation of this face is z equals 1 minus y. Now, for us to set the limits up of this triple integral, what we need to do is we need to say to ourselves, okay, for each point in the projection of that solid kind of fourth of that we're looking at right now, I'm just putting a generic one there in orange, we're going to let z vary from the bottom, which is z equals 0, up to the top, which is that face we just found the equation of. Alright, so we're going to let z vary from z equals 0 up to the top, which is given by the equation we just found, z equals 1 minus y. We also need to take note that the projection into the xy plane is something we need to worry about as well here. This is going to look like this triangle that I'm outlining here in orange over top of the red and the blue there. This line right here in the xy plane is the 45-degree line, so that's the line y equals x. Over here, this will be the line y equals negative x. Okay, so it's going through the origin with slope 1 and negative 1 respectively. So when we look down at the projection of the xy plane, we're going to be looking at that triangle. Alright, so let's draw that, and then we'll get the integral set up, and then we might have to work it out in a second video. Alright, so looking at that projection into the xy plane, what are we looking at here? We've got y equals x, y equals negative x, and then y equals 1 is going to be the top of this. Alright, so, and what we want to do is we're going to vary x between negative 1 and 1, and for each generic x, I'll just put 1 on here, we're going to let x vary. Hold on a second. We got to think about how we want to do this problem. Do we want to do it with vertical slices or with horizontal slices? Alright, I'm just going to wrap up this video by saying it's going to be better for horizontal slices because the bottom changes from y equals negative x to y equals x as we cross x equals 0. Alright, so in part 2 of this video, we'll finalize this by redrawing this region and setting this up using horizontal slicing. More to come.